Control of separation processes. Adiabatic flash, degrees of freedom, modernized perspective. Separation processes, particularly flash operations, remain core unit operations in modern chemical plants. With increasing focus on energy efficiency, automated flexibility, and tighter product specifications, the control of flash units must be approached not only from a mechanistic viewpoint, but also with an emphasis on real-time responsiveness, digital diagnostics, and integrative process control architecture. Understanding degrees of freedom, OF. In process control design, the concept of degrees of freedom, DOF, refers to the number of independent variables that can be manipulated to achieve desired control objectives. For an adiabatic flash, the DOF analysis determines how many process variables, such as flow rates, pressure, or composition, can be actively controlled given the process constraints. In a digital DCS environment, DOF assessment supports decisions about the number of control loops required, the most effective manipulated variables, inventory versus quality versus throughput control prioritization, process modeling for APC and optimization layers. Adiabatic flash system overview. An adiabatic flash unit performs phase separation, typically vapor-liquid, based on equilibrium at a fixed energy condition, no external heat input. It consists of one feed stream, two product streams, liquid and vapor, no heat duty, Q0. This results in a thermodynamically constrained system where pressure and temperature are interdependent at equilibrium. Detailed analysis. Let's define the DOF using a modern control system framework. Unknowns. Each of the three streams, feed, liquid, vapor, has unknown flow rate, temperature, pressure, and composition. For C components, unknowns equals 3, C plus 2 equals 3C plus 6, equations constraints. Attachment C material balances, C equilibrium relations, vapor-liquid equilibrium, one energy balance, adiabatic constraint, one temperature equality between phases, one pressure equality between phases. Total constraints equals 2C plus 3. Degrees of freedom raw, Shri equals 3C plus 6, 2C plus 3 equals C plus 3. However, in practice, feed conditions, composition, temperature, pressure are usually fixed or measured accurately. That adds -C plus 1 knowns, reducing the control-related degrees of freedom to degrees of freedom, net for control equals C plus 3, and since C plus 1 equals 2. Implications for control strategy. With 2 degrees of freedom, the adiabatic flash system allows active control of one strategic process variable, e.g. pressure, which influences equilibrium, one throughput or flow rate variable, e.g. feed or product rate. The third flow, usually the remaining product, becomes the inventory balancing stream, assigned to level control to maintain material balance. Modern control systems implement this structure using flow controllers with adaptive tuning for feed or product regulation, pressure control loop linked to either overhead vapor valve or back pressure regulator, level control using cascaded loops to ensure hold-up stability. These loops are often embedded within model-based supervisory control layers, which adjust targets based on production plans or energy constraints. DOF in digital control environments. In advanced plants, DOF analysis also feeds into constraint management for real-time optimizers, RTO, APC, digital twin modeling to validate control logic and equilibrium responses, AI-based recommendation systems for control scheme selection and performance prediction, process simulations for scenario testing of variable pairings, e.g. feed versus pressure, vapor versus composition. Summary. An adiabatic flash system, though conceptually simple, requires a structured control approach grounded in a clear understanding of degrees of freedom. With two controllable variables, strategic and operational priorities must be reflected in loop design. In modern DCS environments, this means integrating DOF-based decisions with smart instrumentation, adaptive control algorithms, and simulation-backed validation, ensuring robustness, agility, and profitability in separation operations. Adiabatic flash examples, modernized control strategies. With 2 degrees of freedom available in an adiabatic flash system, modern control systems must strategically allocate control loops to maximize stability, product quality, and throughput efficiency. Selecting the appropriate manipulated variables depends on process objectives, such as pressure stability, phase balance, energy efficiency, and composition control, and the dynamic behavior of the unit. In modern DCS environments, smart controllers, enhanced diagnostics, and digital simulations enable better informed decisions about which flow variables and constraints to control and how to minimize loop interaction. Control configuration examples. Each example below demonstrates a valid configuration using two active control loops, one typically for a flow rate, throughput, and the other for pressure, strategic constraint. The third stream is used for inventory regulation, typically via level control. Tashrat 1, feed rate and pressure control. Control actions, feed flow rate, controlled to regulate throughput using a mass flow controller or smart valve. Pressure, controlled using a vapor outlet control valve or back pressure regulator. Liquid level, maintained by adjusting liquid outflow via level control loop. Modern considerations. Ideal for systems where feed variability is expected and pressure influences product separation quality. Integrated into APC platforms to match upstream production rates. Valve characterization and flow meter calibration are managed through smart diagnostics. Performance. High controllability with predictable dynamics. Potential interaction. Increased vapor release for pressure control affects flash equilibrium and holdup, compensated using decoupling logic or model-based feed-forward. 2. Vapor rate and pressure control. Control actions. Vapor flow rate, actively adjusted to maintain vapor recovery or align with downstream compressor demands. Pressure, maintained via adjusting feed rate or heat balance indirectly. Liquid level, controlled via liquid outlet. Modern considerations. Useful when vapor output is economically or environmentally critical. Flow loop integrates with mass balance and composition tracking models for quality prediction. Enhanced loop tuning or MPC may be needed to handle pressure-vapor interaction. Performance. Good responsiveness, though highly sensitive to vapor-liquid equilibrium shifts. Integration with downstream vapor recovery systems improves stability. Liquid rate and pressure control. Control actions, liquid flow rate, actively controlled to ensure consistent withdrawal or product blending. Pressure, controlled through vapor outlet or utility back pressure regulation. Vapor holdup level, managed via feed or vapor valve. Modern considerations, effective in systems with downstream blending, storage, or purification units. Smart valves support precision control and diagnostics to handle low flow regimes. Ideal when temperature control is indirectly influenced by pressure. Performance, strong decoupling between pressure and liquid level loops. Stable under moderate disturbances. Highly tunable with standard PID or adaptive tuning modules. Indirect flow control or alternate loop designs. Using feed-forward logic to control feed based on vapor or liquid demand. Implementing ratio control between vapor and feed to manage split fraction stability. Using level override control to prioritize safety in overflow conditions. Modern considerations. These advanced configurations are managed through function block diagrams, FBD, or SFC logic in the DCS, often modeled and tested using digital twins to predict loop interaction. Alarm integration ensures early detection of loss of control authority or valve saturation. Loop interaction and optimization. Modern DCS and APC systems assess control scheme interactions via loop interaction matrices, measure the degree of coupling between manipulated and controlled variables. Control performance indexing quantifies responsiveness, overshoot, and variability. Model predictive simulations test control schemes under different disturbance scenarios. Smart diagnostics embedded in controllers continuously monitor these performance metrics and suggest reconfiguration or retuning when necessary. Summary. The control of an adiabatic flash system, while seemingly simple, can be optimized through careful selection of flow rate and pressure control loops, underpinned by a solid understanding of degrees of freedom. Modern tools like APC, auto-tuning, smart instrumentation, and dynamic simulation allow for greater control precision, disturbance rejection, and system transparency. Choosing the right combination of control variables in line with process objectives enables efficient, stable, and economically optimal flash operation. Non-adiabatic flash degrees of freedom, modernized process control perspective. A non-adiabatic flash unit represents a more dynamic and versatile separation system than its adiabatic counterpart, incorporating an external heat input. typically via steam, hot oil, or electrical heating to control thermodynamic conditions. This added manipulability increases the system's control flexibility, but also introduces greater complexity in loop interactions, energy balance, and stability considerations. Modern DCS platforms, advanced diagnostics, and integrated modeling tools make it possible to design and implement precise, real-time control strategies for non-adiabatic flash units. The foundation of this control logic lies in a clear understanding of degrees of freedom, DOF, which guide the number and type of variables that can be actively managed. System description. A typical non-adiabatic flash unit consists of one feed stream, two product streams, vapor and liquid, one utility stream, heat input via reboiler or heating coil. This adds a new variable, the heat duty, which directly influences the vapor-liquid equilibrium and offers greater control over separation quality, product ratio, and energy efficiency. Hash degrees of freedom analysis. In control system design, DOF analysis determines how many independent process variables can be actively manipulated to meet desired specifications. Unknowns. Three process streams, feed, liquid, vapor, each with unknown composition, temperature, and pressure, press one heat input stream. For C components, unknowns equals 3 times C plus 2 plus 1 equals 3C plus 7. Equations, constraints, Stein is C material balances, C vapor-liquid equilibrium relationships. One energy balance includes heat input, like one equality for product temperature, one equality for product pressure. Total constraints equals 2C plus 3. Initial degrees of freedom. DUF equals 3C plus 7, it's 2C plus 3 equals C plus 4. After fixing feed conditions, composition, temperature, pressure, C plus 2 constraints applied, net DOF equals C plus 4 and C plus 2 equals 2. However, the heat input adds another manipulable variable beyond the adiabatic configuration, giving a total of 3 active control degrees of freedom. Implications for control design. With 3 degrees of freedom, the non-adiabatic flash system allows independent control of one throughput variable, typically feed or one product flow, 2 strategic variables such as operating pressure affects phase split and vaporization, temperature affects composition and vapor fraction, product composition ratio, vapor to liquid or vapor to feed. The 4th stream becomes the inventory regulating loop, typically a level control to maintain material balance. Modern DCS integration and advanced capabilities. In modern control environments, the added degree of freedom enables tighter product specification control by dynamically adjusting heat input to control flash temperature, energy efficiency optimization by modulating reboiler duty based on target separation or external utility costs, multivariable constraint handling via APC or MPC systems that manage temperature, pressure, and split fraction simultaneously. Dynamic safety protections, where excessive pressure rise or overheating can trigger preemptive shutdowns via SIS integration. Real-time control schemes are validated using process digital twins, with controller parameters adapted through performance benchmarking or AI-enhanced tuning engines. Key design considerations. Interaction between loops. Increased heat input raises vapor rate, which can affect both pressure and liquid level. Feed-forward decoupling or gain scheduling may be used to reduce cross-loop interference. Modeling complexity. Dynamic models must capture heat transfer, phase equilibrium, and nonlinear behavior, especially near phase boundaries. Smart instrumentation. All control loops should be paired with SIL-rated transmitters, smart control valves with diagnostic feedback, and utility flow meters with verified rangeability. Digital commissioning tools. Loop behavior under different control pairings can be simulated to identify optimal configurations before field tuning. Summary. The non-adiabatic flash unit with 3 degrees of freedom offers enhanced control over key separation variables through the inclusion of an active heat input. This expands the design space for control engineers, enabling advanced strategies for quality, efficiency, and responsiveness. When implemented using modern DCS and APC tools, the unit becomes a flexible, high-performance separation module, adaptable to changing production demands, energy costs, and composition targets. Understanding the degrees of freedom is the first step toward unlocking this advanced control potential.